Clouder discussion channel to ask questions or make remarks on the talk. And we'll take these questions after Yannick's talk, one after the other, unmuting you to allow you to ask the questions live. Meanwhile, please remember to keep you muted and enjoy the talk. Yannick?
Actually, I don't have the right anymore to share my screen.
Okay.
Before, so.
I don't think I have the right to grant you this. Amin, can you do it?
Amin, maybe?
Yeah, you should be able to.
Here it is.
Yes.
Thanks. Yes. Does everyone see my slide? It should be full screen. All right. Okay, so let me first thanks, of course. Sorry? That's full screen?
We're seeing, there we go.
There we go. Okay, awesome, thanks. All right. So thanks a lot to Amin and Asia both for organizing this workshop and giving me this opportunity to tell you about some of the work I've been conducting with many co-authors that I will come back to later, of course. Just for context, I'm currently a researcher at INRIA, but I still put the pen affiliation as it's work that I started when I was a postdoc with Steve at UPenn, and that I'm still actively developing with many people at UPenn in particular. And also let me emphasize that indeed you can ask questions in the Clouder chat room, and please feel free to do so as even virtually you've been kind enough to commit to a room when I'm wandering for an hour. So feel free to interrupt me. I will try to take questions on the fly when adequate. So, all right, this being said, what is this talk meant to be about? I'm titling this Verifying Compilers through Equational Means, which is not necessarily the most apt title to develop to describe everything I will tell you about, but there's at least one advantage is to already phrase that it's going to be about verification of compilers, and that we will put an emphasis about proof methods to do so. To try to exactly phrase where I'm coming from with this work, I will start at the quite high level, so please bear with me if it's a bit hand-wavy at the beginning. We will get more precise and technical afterwards. We just coined what is verified compilation at an extremely high and abstract level. The point of it roughly is to consider two languages arbitrarily distinct, have some kind of compilers or program transformations that goes from one language to another, make sure that we have our formal semantics of each language, and somehow to prove that the transformation is correct in the sense that there is some kind of refinement of behaviors that coins the fact that the transformation is semantically preserving in some sense. And of course, it's a very active field of research, at least for the last 10 to 15 years. There is a lot of activity about trying to tackle new programming constructs, new kind of optimizations. For instance, this year at POPL, you will hear about verification of a just-in-time compiler, which, as far as I know, will be the first time. And also, there's a lot of work about trying to precise and to extend what means this refinement of behaviors on the domain of application that's that, in the sense that can we tackle or not open programs? Can we tackle dynamic linking with different programming languages? Or also, can we preserve more in the semantics, maybe security properties, for instance? But what I will talk about today is not things as fancy as this kind of complex refinement results, but more trying to ponder how the way or the methodology that you use to define the formal semantics of your language impact kind of this big picture. So how do I define formally this semantics of L1 and L2? What does it mean for the formulation of the refinement theorem that I want to coin to express the correctness of my compiler? And finally, maybe more importantly, how does it impact the proof methodology that I will use to prove this refinement? That's kind of what we are going to discuss. And in order to, once again, give some context, I will start with what you're probably all familiar with and must be the most influential work in the domain, especially the Coq community, of course, is CompCert, so this fully verified end-to-end C optimizing compiler that was developed at INRIA for the last 10 years, roughly. If we come back to the three components we discussed just before, what CompCert does is to use this propositional small-step operational semantics. So essentially, you have some kind of notion of state that encompasses the syntax of your program on your memory. And you have a small step transition that explains how a state transits to another one and how it emits as it does, so potentially some kind of observable event. Crucially, it relies on prop, so that it's extremely convenient to write, it's extremely easy to write, and it's extremely expressive. What goes with that is this notion of inclusion of traces of observables, so you can trace all these little events that happen during your execution, and you will express that you are in a termination sensitive way, making sure that the result of your compilation is able to exhibit only traces that the source was also able to exhibit. And the last component is how do you prove this kind of stuff? CompCert use old methods, but popularize them and make them formal by using this kind of elementary simulation diagrams, where basically we can have elementary little diagrams that can simulate, that explain how, depending on the kind of state you start from, you are able to simulate the source with the target. And there's, of course, if we go into the details, many kind of simulation diagrams. There are subtleties about whether it has to be forward or backward, but I won't get into this detail. Just what I want to coin is that it introduces this very pervasive proof method that is extremely efficient, where you're going to prove your diagrams, and at the top level, you're going to conductively stitch them together to obtain your refinement. So this has been a huge success. It has been extremely pervasive. Not that there are not alternative approaches that have been tried, but it's hugely the most popular ones. And what I would like to discuss today is an alternative to these three components. I want to make clear that I am not trying to bash CompCert in slightest, because we are nowhere near yet having such impressive results as what they have developed. But there are three extremely well-known problems with this approach. These problems that are well-known beyond the creation of verified compilation, that are basically as old as semantics, which are that this kind of operational small set semantics like compositionality. And this hurts your proof technique, particularly in the sense that when you're going to write your diagrams, you're going to craft this simulation relation, and you're going to be forced in this simulation relation to express how the syntax at each component, at each level of your compiler relates, or alternatively, how the program counters that explain you where you are in the execution of your program relates. This kind of bookkeeping details that are extremely complex in practice and extremely annoying to keep track of. Second problem is the lack of modularity, which basically is to say that all the effects that your programming language may have are kind of mixed together in this single transition relation. And this tends to hurt maintainability because it hurts the separation of content that you might want to have when you are iterating over the process of developing your programming language. And the last one is the lack of executability, sorry, in the sense that, of course, fundamentally you rely on prop, which is a huge benefit because it makes so many things so much easier. But in exchange, if you were to want to do testing on your semantics, which even it can seem at odds with the idea of doing formally your programs, is crucial when you're iterating on a realistic programming language. But then you have to write separately an interpreter, and you have by default no guarantee that there is any relationship between this interpreter and your formal semantics you want to reason about. So it hurts testing. So what we will see together is one solution that we propose to prove compiler with similar correctness results as the one we set, but with an approach, a semantic approach, that will cover all three of these properties. Of course, I want to kind of tell you the science, explain you what are the ideas behind. But since I have a whole crowd of Coq developers in front of me, my hidden agenda is to sell you two libraries, two open source libraries that I've been contributing with many co-authors to during the last couple of years. The first one is the library of interaction trees that is available on GitHub and open. And if I coin it in just a few words, it's basically a generic toolkit that gives you all the tools you need to define semantics and to reason about these semantics of interactive systems in the very, very broad sense. The good property that it helps you achieve is, once again, this compositionality, modularity, and executability. And it will come with many tools to reason, and in particular to reason in a completely transparent way, in a termination sensitive way. We will see how this idea of doing top-level conductive stitching of little diagrams is irrelevant here, because intrinsically we will work in a conductive data structure, and we can conduct all this reasoning in an equational way. Let me just emphasize that today I take the angle of verified compilation, but this library is in no way tied to verified compilation in particular. Any formal reasoning you want to do about any kind of interactive systems can benefit from it. The second library that I want to sell you is Velum. Velum is a formalization of the partial, of course, formalization of the LLVM infrastructure that is also available on GitHub, not yet on open, but we hope to make a release soonish. You might have heard of Velum already years ago. So it's a project that Steve has started quite a long time ago, in 2012, I believe. So we still run it as Velum, but it's kind of a Revelum with a complete rebuild of its semantics on most of its infrastructure, but keeping the same goals. What are the selling points? We're going in particular to provide the formal semantics for the sequential intermediate representation of LLVM that inherit these good properties from the I trees. So this time the semantics is defined from the I trees. We will see that we derive from it some interesting reasoning principle to verify program transformation about this language. And in particular, we validate them with a large case study. And we like to think that this gives a foundation to be a quite exciting playground for original semantics introspection into verified compilation. All right, so this is kind of the high-level idea. We're gonna jump into it, but let me mention that I'm going to tell you kind of like a, I hope, self-consistent and understandable story, but this story will actually span across 3 pieces of work that many people have contributed to. So let me sum up in one slide these contributors, even if it's slightly approximative. The first thing has been the development of interaction trees that was published last year at POPL. In particular, let me underline that Liao Chia was a lead designer and developer. It had a collaboration between UPenn and also Bedrock and Seoul University. Then came the refoundation of Velum, where Kelvin Beck and Ian Yoon, that are 2 PhD students, join us. And finally, Vadim Zaliba and Ilya Seichuk join us with the HELIX project that we'll come back to at the end, and have since then contributed a lot to Velum itself as well. So it's not a clear separation, but just to give you a broad picture. Right, let me now jump properly into what I want to tell you about more formally. Okay. So the starting point, we can have 2 phases. We're going to define a semantics, then we will see how we reason about this semantics. Let me start with defining a semantics for VIR, so standing for verified IR, which is the intermediate representation of LLVM, using interaction trees. But first, before talking about VIR itself, let's have a little primer about what are interaction trees, what they are. At its core, an interaction tree, it's a data structure in Coq that is provided by this library. And the point is that any value of this data structure is meant to represent a computation that is shallow embedded in Coq. So to do so, what we have is this I tree that is parameterized by two types. That is co-inductive because, crucially, we want to shadow embed potentially diverging computations, on which as a return type as parameter R, so like any of the monads that you might be used to, that in particular can therefore be a pure computation that just returns value of this type of R. The other parameter that is R is this type family E, that is the set of events. You can think of it as effects that your program may emit during its execution. Take this as a parameter, and at any point, it's able to emit through the this constructor one of these events. And because the events are a type family, you can find in the type of the event the nature of the answer that you assume your environment will give you back to as a response, that you can continue your computation with a continuation index by this type. And finally, there is this tau constructor, which basically represents an internal step that you do not wish to observe. Let me just add two remarks before making this a bit more concrete. The first one is a very technical detail, which is here. It gives you the positive style of inductive, but the implementation is negative. But this doesn't matter for a user of the library. The other aspect is that this echoes lots of previous existing works. It's basically a co-inductive implementation of the FREE monad. So if it rings a bell, or if you feel like it's something you already know, then it's absolutely normal. All right. So if we try to be a bit more concrete about what is an intelligent tree, we are trying to sum up in one slide the broad idea about using them to represent computations of programming languages. Here, you have a little tree, hence the computation. Basically, does a write in memory that writes 1 to x. Since writing doesn't expect any answer, just has a continuation index by unit, we follow by doing a read to this location. When you read something in memory, here I assume that you expect a natural as an answer. So you get a continuation that is indexed by n, by nat, sorry. In each branch, you can do different computations. So here you will write in y whichever answer you get back. And finally, you will return the same value. So this is a tree, but notice that intuitively, if you think of writing reading in memory, you assume that quite obviously if you read x after having written 1 in it, then you should only have one solution in your continuation, which is the one where you will lie. So the point is that interaction trees before interpretation then don't assume the semantics of your events. That's exactly the algebraic effect approach, if you're familiar with this. And so say the second phase that is crucial in the process of giving meaning to computation, which is the phase of interpretation, where the idea is to introduce this time the semantics of these effects that are so far syntactically represented in a tree. To do so, you will define a handler that explains the meaning of the effects, and the library will provide you an interpreter that will lift this handler across the whole computation. So for instance, here, the natural simple implementation of read and write events is to use a state monad, where you will consider some kind of implementation of your state. And you see that given an initial state, you get a new computation, so still an I3, but this time you only have, so void E, the empty set of events. You have eliminated from your tree these memory events, and you get now product type as a return because you get your state. So this time you get something that you can execute, but of course not inside of code because it's co-inductive, although you can force its execution with some fuel, but in particular you can extract it to a kernel to run it. Now to complete the picture, if you were to start from some syntax, from some language that you want to represent, you first have a phase of representation of your syntax as a tree with event, followed by the interpretation. So that's the broad picture. And we will discuss how to do this for a realistic language, such as LLVM IR. Once again, if at any point it's unclear, please feel free to interrupt me either through the chat or any other means.
Yeah, I have a question.
Yes, please, Ralph.
Yes, thanks. So one thing I'm a bit confused about is this. If I see it correctly, this E thing has a type which is type to type.
Absolutely.
The memory E here, right, has type to type.
Yes.
So it's like a container or something. How do I like that? That doesn't entirely match up in my head with the idea of how I would characterize an event and the response from memory, where I would expect, like, I don't know, like have a unit or a natural number depending on whether it's a read or a write. So how does that work?
So memory E. Okay, memory E is you're going to define it as a variant, which will have several constructors. One constructor per type of effect that you can have with your memory. So here there would be two types of effects. There would be reads and writes. And the point of memory E being a family of type, being from type to type, is because each constructor will reflect in their type the nature of the answer that they expect. If you see here, I was able to, after write, I was able to type check my tree with a continuation that is indexed by units, because the type of write x1 is memory E of units. In contrast, the type of read x is memory E of nat, that I have access to this nat, so that I know how to type my continuation. Does that answer your question?
I'm still a bit confused, but I think maybe at some point we'll have a more concrete example. I don't know. Like I can't match on the argument type, right? I can't do a case distinction on the type I get in. So somehow I'm missing something where you're matching on the event type.
Well, if you come back to the type of the data structure, maybe if you look at this is existentially quantified by this X type, which appears in the type of your event E. So when you do an event, you know statically the type, the nature of the continuation, which is the nature of the answer that the environment has responsibility to provide you. If you want me to go over it again, please don't hesitate, or otherwise I will move with it and we can try to resync later.
Yeah, I guess we can come back to this later if it's a problem. Thanks, sorry.
No, absolutely no worries. Thank you for the question. All right. Right, and so my point here was that it kind of gives you a general recipe when you want to use I-trees and you want to define semantics for your language, which is, of course, right on the syntax, so that's the first step. But then you go through a phase of making an inventory of every effect that intuitively your language should have, and to each effect will correspond an event interface that you will be able to combine together into a single interface. Then you will use the I-tree combinators to represent L as non-interpreted I-trees over this interface. And the idea is that the combinator are expressive enough so that in many cases you're able to get the compositionality that you're looking for at this stage. Then you get a phase where you handle each of the events that you expect to be implemented into some appropriate method. And it will give you an interpreter for your whole program. And here's the fact that each of the category of events, imagine your memory, your local state, and so on, can be implemented separately. You get some notion of modularity. And finally, if you have interpreted all of your events in particular, you are able to extract the resulting tree to a camel and to actually run it with a little driver. So that's where you get the executability. That's the rough plan, and let me move on to the intermediate representation of interest. So LLVM, I assume most of you are familiar with. It's this like huge compilation infrastructure that is kind of a success that it came from academia, but definitely became a huge industrial project. And in particular, at its center, it has this typed intermediate representation that has a fairly well-defined, although not completely, semantics, upon which many analysis and optimization can be performed. If we describe it very roughly, it's at its core, it's a control flow graph-based language, which happens to be SSA. But it has also some more involved semantics issues to manipulate notion of undefined values and poison. That's some kind of system calls, various notion of external calls, intrinsics, and internal calls. It has a non-trivial memory model. In particular, it allows you to do pointer to integral cast, sorry. That's some involved access into structured data, which is all notions that are non-trivial, but we know how to reason about. However, it got tricky when we were starting to keep track of things and reason about it modularly. What do I mean by that? I mean that, as mentioned before, the project existed before I started to join in, long before it, and was a success. There were already many works, notably by Joe and Steve Undef, that managed to perform impressive achievements in this language. So the semantics was fully defined. They were able notably to do complex reasoning about the SSA form by computing the denominators. They verified impressive optimizations such as softbound or instrumentation. They even verified mem-to-reg. However, the project was kind of stalling. They said that it was becoming extremely hard to maintain it and to have new users for it. And part of it goes back to these semantics issues. There are several reasons, but part of it goes back to semantic issues, which is that even worse than having a small step operational semantics, in the case of a CFG, you have a semantics that is parameterized by your global graph, and you maintain a program counter that tells you where you are in the graph. So that if you do an optimization that changes your program, you're literally changing the semantics with respect to which you're reasoning. So you're really not compositional. Oh, that's clean. And so the point is now to start with Steiner basis. So EIR is this rebirth, where we're going to just follow a recipe and give a semantics to EIR. So let's start by inventorying the effects. So we're going to take like this small factorial, as always, as an example. So this is essentially a function in LLVM IR. We take a few looks, we can see that there is like some arithmetic, some local computations that are going to be loaded in local variables. So first kind of event that we want to represent is this interaction with the local memory. So what does it look like concretely? This is just a snippet of code from the development. So as I was mentioning it, Ralph, we have here this local variant that is a family of type with two constructors. So write is indexed by the location that you want to write to and the value you want to write in it. And you represent the type that you don't expect any answer, so it has type locally of unit. The read, however, you expect the local state to return you a value, so it has type locally of two value. That's really where you use this index type. Sorry, focus. If we continue similarly to local state, there is a notion of a global state. One point that I just want, it's a bit of a technicality, so you can forget about it if you don't ring a bell, but note that there is a whole design space, where in the sense that it's extremely arbitrary that I decided that global states and interaction with them should be modeled as effect. While this arithmetic, I'm not modeling that at any event. To add two numbers could be an event itself that would be implemented separately. Currently, we put the cursor at expression should be computed at representation time. But note that this is arbitrary and there is, I think, some thinking to be made as to what is the best solution. We just continue with what we've done. We can see that there is, of course, memory accesses. So we model interaction with the memory model through, once again, an interface, which, of course, is a bit more complex this time. We won't go through it in detail, but we have to manage frames that we want to push on top during function calls and returns, allocation, load, store, get element pointer to access structured data, and this cast from integer to pointer. We keep going. We have this return operation, so we need to handle function calls. So there is function calls as events. It's actually technically gets refined into three notions of function calls for details that are to do with LLVM itself. Stack of local frames that you want to push on top during these calls, but also a notion of non-determinism. That's a big pain point about the semantics of LLVM IR. Undefined behaviors, that is related. We'll come back to it in a second. On some utilitaries, we are able to instrument our semantics with debugging events and failure. So let me just take 1 minute to give you a little feel. Oops, sorry, I have a bug in my slide. about this notion of Undef and undefined behaviors and why it entails some non-determinism. It's a complicated story that many talks has made about in details. Let me just give you a very rough idea. The notion of undefined behavior is related but slightly different to the one in C, where essentially one way to put it is that as an intermediate representation for a compiler, there are some errors that you assume have been handled at a higher level, and it's not your business neither to check it dynamically nor statically. We represent this as undefined behaviors. And as far as the compiler is concerned, what is meant for it, so don't assume anything about our compilers, is that they can assume whatever they want if it helps them to their optimization. So how do we model this? We model this as with this event, undefined behavior, whose return type is void. So the empty type. And the point of modeling this with the empty type is that you're able to follow this with a continuation at any type. It just has to eliminate the void type that you get. This allows you to actually model the fact that the compiler will be able to substitute an undefined behavior event with any computation that it chooses. Then comes a trickier bit, which is if you want to have this notion, but also to enable some kind of speculative execution, you need to have intermediate values that do not crush the computation in a sense, but are slightly undefined. So that the notion of Undef and also poison, but I did it out here. And Undef has some weird semantics because essentially it's typed, can act like a random variables. Every time you poke at it, it can return you any value of this type, but it has no obligation to return the same thing twice. So in particular, it's not true that Undef plus Undef is the same as 2 times Undef. So the right-hand side is going to be even, but not on the left-hand side. So what we do currently is to manipulate the notion of U-value, which extends the domain of dynamic values with this notion of Undef and some symbolic expressions about them, so that as long as we're concerned, we just keep the symbolic expression, which represents a set of values. And when we interact with something, such as an external code that really needs to have something concrete, that doesn't care about this nonsense about Undef and so on, then we have an oracle that concretizes as we need. That is some kind of peak event that, given a U value, will give us one valid D value. And we defer the implementation of this oracle to the handler of this event. So once again, we have a nice separation of concerns. Right. So this is an aside, which has to do with more semantic technicalities of LLVM IR than with I3 itself. Let me wrap up this inventory. So through this step, what we did is kind of like look deep into the eyes of our language and say, here are all the events that it might cause. Let's inventory them, and let's package them with these little combinators that the I3 will give us into a single interface. And now we can start representing our syntax as strings. Let's go. So what do we want to do once again? The point is that we want to do things compositionally. So we have to look at the LLVM program. We have different syntactic components. We have expressions, we have instructions, terminators that compose blocks that are composed together as control flow graphs and that are mutually recursively referring to each other to form a program. And we are going to build the meaning of each of these components by recursion on the structure of syntax. We're going to compute these representations. And in particular, we're going to have the benefit that any subsyntactic component can be represented as a tree in isolation. You don't have to do things globally. You can talk about open programs quickly, transparently. And to do that, we're going to code monadically, so the I3s are monad. We're going to use fixed point combinators to resolve our recursive equations. I won't, of course, give you the full representation of LLVM IR, but let me try to pick a few examples to give you a feeling about what it looks like. Here, we have this representation function for instruction. So I is an instruction. We're going to represent it as an I3 over this interface instruction E that returns unit. So it returns unit because an instruction is purely a side effect. It's not meant to return a value. We're going to match an I, and we have one case per kind of instruction. So here, for instance, a lookup. So OP here is some kind of expression, and we want to put the result of this expression in the identifier ID. So the first idea is that once again, we are able to denote each component in isolation. So we are able to represent separately the meaning of expression as an I3, that we can call this representation function. We get an I3. I will gloss over this translation, which has to do with slightly different interfaces, so just to embed a smaller interface into a bigger one. But then this I3 might even be infinite as far as we know. The computation might diverge. But since we are into this co-inductive monad, if it were to terminate, we would get back some dynamic value that we're able to use to trigger an event. So triggering is basically building the smallest computation that just do an effect. So here, for instance, I'm triggering X. So I do the visible event read X, and then I just return whatever is given back to me. So here I have implemented, in a sense, as an interactive computation, the meaning of loading the value of an expression in a variable for LLVM. We just go quickly over a couple of other examples. So to allocate something, I simply trigger the allocation event. It should give me back some kind of value that I will write to my local state. So I have two triggers. So when you load, so things can get a bit more complicated, but that's kind of the satisfying part, which is it scales to complicated case without any issue. To load is to first use my representation of expression to get a computation that will give me the pointer to look at. Monadically, I get UA this address. The problem is that, as we discussed, actually I might get a set of address because of Undef. So I'm gonna ask my oracle to pick one for me. I get DA with well-defined address. Now, I actually have still technical issues, but it's really semantic issues that as someone modeling LLVM I want to care about, which is actually this address might be this weird poison value. If that were to happen, I will raise an undefined behavior. But if finally I know that I got a valid address, then I'm just going to trigger my load event and write the result in my local store. So this is typically the way you're going to represent your computation as trees. Now, here we just talked about basically triggering on sequencing computation. And since we are shallow, we of course can do any meta-level computations with Coq. But with these simple tools, you can go all the way to denote your blocks, represent your blocks. Terminators, your instruction, your expression, and your sequence, you package everything. However, one technicality, again, that's just for people that are into LLVM. The denotation of blocks is indexed by an identifier of a block, which is basically the origin from which you come from when you interpret things. This is just to do with finals. And the point now is that we want to resolve the jumps, however, and that at this point we need, of course, a new tool, basically because it's the first time we encounter any notion of recursion, of potentially dynamic computations already. And to do so, the I3 library gives you a variety of fixed point compilators that solve this kind of thing. So I'm being quite slow, so I will skip over it fairly quickly, but please ask questions whatever you want if you want more details. But essentially here we use the iter combinator that tells you, assumes you have some body that do a computation and either returns you a new value of your accumulator, or the little flag that say I want to go back in my loop, or a result on the flag that say I'm done. Then the combinator will close the nut and internalize the recursion. You don't see the accumulator in the return type anymore. Of course, maybe you diverge, but once again, it's internalized. So the point is that we can use this iter combinator to resolve the jumps, where, roughly speaking, the idea is that if your notion of accumulator is a pair of the block ID from which you come from, for the finals, and the block ID that you want to interpret, The return type is either you jumped out of your subgraph because you want to return open programs, therefore you return a new pair that have to communicate with another piece of code, or you return from your functions, you return a value. Let's not read it, but the implementation is fairly straightforward, just a matter of looking up in the graph to find your box. All right, so I hope this gives you at least a little taste about how it looks like to use iterates to represent this kind of semantics. And now that we have this representation of computation as non-interpreted trees, once again, not executable at all at this point because all these events are non-implemented. I still don't know what is my memory, I still don't know what is my local state, and so on. But now we can actually give a meaning to this effect. We can implement them in terms of components. Let me give you a very simple example. For the locals, for instance, remember that it was this variant with two constructors. Let's implement them as a simple finite map. What does it mean? That means, that means that you want to each of event of type local E to associate a computation in the state monad. So if you look at the right, for instance, where it's going to be a trivial computation that just return the updated map on unit. So exactly what you would have done if you ever touch state monad, nothing fancy, except that you have to be careful on the wrapped on top of the I3 monad, basically because you always need to live in a monad that can internalize divergence. So this is a complete local definition that just talks about locally. On what the library gives you is this inter combinator that lifts this over the whole tree by crawling the tree and substituting any calls to external events by their handled version. Here I have used a bit the notation compared to what is actually in the development, but intuitively, part of the signature has disappeared. You have the local events that are not there anymore at this point. So you get closer to being executable. If we step back, what happens in PELU, what happens in VIR, is that we chain such handler one after the other, starting from this structural representation that we discussed before, handling away something that is called intrinsics, calls to some kind of peculiar function that has a well-defined semantics, interpreting away the global environment. So we introduce a new piece of state, interpreting the local environment, new piece of state, interpreting the memory model. So here, new piece of state, but note that I keep this opaque, but here you have basically a wallpaper behind this little handler. That's a model, a memory model that is based on one part on the CompCert memory model, in the sense that you have this notion of blocks on offsets, but that also has a dual representation that is lower level, so that you can deal with this conversion from input type to tablet. And then there's something that gets a bit more fancy, which is that, as we discussed, intrinsically you are non-deterministic, which makes things much more complicated. So as far as possible, we certainly model non-determinism by getting out of just this state of I3 monad, and instead of this time getting into prop, which is kind of against what I've told you from the beginning. But we have to do that because we want to capture essentially specification of sets of valid implementation, which is pretty much what LLVM IR is. But I still stand by what I told you about my desire for executability, which is that by sharing all this up apart, we can give alternate implementations, alternate handlers that are executable, that will pick only one possible implementation. And the interesting part is that this takes very little code to derive this interpreter. It shares most of it with the model. And we can, for free, derive, well, for free, once the meta square is there, of course, obtain a refinement proof that the interpreter that we have is one of the valid behavior of the model. To conclude kind of this semantic part, what we have is in particular an interpreter that we can play with. With some GitHub, we can install it easily. And that takes valid LLVM IR syntax as input. Maybe have a little front end in the camel. Then I use the extracted code to represent this as an I3 and interpret away the events. And then it goes back to a camel with a tiny driver that just crawls through the tree. In particular, in this tree, what may still be there are external calls, debugging messages or failure. But if it doesn't find any of those, then it will return you the value. Let me emphasize that it's a realistic subset of LLVM IR, although sequential, we don't cover concurrency. And that if you're interested by doing practical things with LLVM, we are happy to take any feature request to extend anything we would do. All right, I've been, of course, much slower than we'd like. So let me quickly talk about relational reasoning about this semantics. But please still interrupt me if anything wasn't clear. All right, so how do we reason about these objects? The first part is, let's not talk about VIR yet, not talk about Pelum yet, but just about I3s. What does the I3 array give you? It gives you a co-inductive relation that will define refinements of computation, ignoring a finite amount of interest step. What does it mean? Straight. It means that if you want to add pure computation related at R, so R is a parameter of the refinement relation, you just have to prove that these results are in the relation. If you want co-inductively to strip taus, you can match taus on each side and continue your proof of refinement. If you meet events, as long as the events are syntactically equal and that you can co-inductively relate every single branches, then you get equivalence results, while refinements. And finally, we mentioned ignoring finite amount of internal step. We mentioned that tau steps are not observable. Do so. This time, it's not a co-inductive line, it's an inductive line. You can strip a finite amount of taus in an asymmetric way at any given point. And so the fact that it's only inductive here is intuitively crucial, because otherwise you would relate the infinite stream of taus to any computation. I won't get into any details about that, but let me stress that developing the meta theory of this object is not trivial, and it was the subject of our speaker paper last year. Now, it's a relation we work with basically on L3, and it has many equations that the library comes with. It has structural laws that tell you two trees, how do they relate fundamentally. It has monadic laws, of course, the one you would expect, that ret is basically a unit of both sides and that bind associative. It has iterative laws, so we saw that we use these iterative combinators, but of course, they just give you a definition, but you can't do anything about it without going back to inductive proofs. You won't be happy. So the library shields you about having to do inductive proofs as much as possible by providing you a set of equations that axiomatize basically the behavior of such loops. So for instance, you can unfold one step of this loop and so on. It has interpretation law, which is like this equation that you have at the top level, you can propagate them through your layers of and the library comes with all the proper instances that you need to actually do proper situated writing, working up to this equivalence. Now, this is basically telling you where computations equivalent, but you also want to prove refinements of computations, saying that two computations of different nature relate in a meaningful way if you want to prove either. And so intuitively, we can have some relational proofs. You can think of this relation as some kind of very primitive relational prime logic. If you want to prove, sorry, this the quality of this picture is terrible, my bad. If you want to relate pure computation, once again, they are just in the relation. Your refinements are monotonic. They are transitive, where you need to combine your postcondition in the meaningful way. They go through interpretation. But maybe more interestingly, you can deal with sequence. So this rule is a bit annoying to read, but if you just rephrase things a little bit with annotation, if you think of T being equivalent to U at R as actually the pair TU admitting as a postcondition relation R, then you get basically the relational rule for the sequence, but enforcing that this rule is termination sensitive. If you can establish this, it also enforces that T and U coterminate, or that it enforces that on the way they are dissimilar in the sense that if you think of external calls for for CompCert, for instance, they will maintain that the exact same external code happen at the exact same point. And so once you have that on I-trees, you can basically lift all this reasoning principle on VIR programs. And the goal is that you forget about the fact to implement it with I-trees, but you reason directly in a rational way, equationally, about VIR programs or VIR programs on the programs of other languages. So for instance, if you have P and Q, two pieces of syntax, you can say that they are equivalent, well, more than Q is a R refinement of P, if when you represent each of them as I-trees, they are equivalent at R. This is, of course, an extremely tight relation. I just happen to do 2 stores in a row to the same variable, which intuitively you know doesn't really matter. You can't establish that these computations are equivalent, once again, because you enforce the simulation of observable events. Intuitively, as far as this relation is concerned, access to the memory can be observed. However, it's already adequate to develop structural equations. In particular, just with this notion of equivalence, you can reason in a compositional way about the control flow graph and about how you can compose your control flow graphs. For instance, the first equations tell you that if you have a disjoint union of two control flow graphs, you can forget about half of it as long as you syntactically, just looking at the syntax of your program, you can prove basically that they are disjoint, that you won't re-enter the first control flow graph. Similarly, you can always unfold them, allowing you to first reason about the first half of your control flow graph, and then thinking later about what will happen. And you can also split them when the control flow are completely independent. So you are able to actually reason about subpart of program, which is something that we are having lots of trouble with this translation of. I'm not showing it there, but there is also a whole battery of structural lemmas that allows you to reason about more pedestrian syntactic questions about the language. The notation of a block is the denotation of the first instructions and the remaining, and so on and so on. All right, but so we can reason about the structure of the control flow up to this very tight equivalence, but it's too precise to reason about instructions. So we will now relax the relation, make it coarser by introducing more semantics. So through this process of interpretation, you can, for instance, define P is a refinement with respect to R one level later. If for any local state, if I represent my program as a tree that interprets the local event, and same for the other computation, so the other program, then I will get this time as an answer both a value that I'm interested in, but also a pair of new local states. And so what I can say is that this program is equivalent if I don't care about the resulting local state, but at any rate, they will still give me results that are related in R. And of course, when you do a by simulation proof, when you do a proof of correctness of your optimization, you will care about crafting the right simulation invariant, but you will always, through monotony, be able to forget about this fact that you used during the proof. All right, so and note that this is can be formally proved to be a relaxation of the previous refinement. So you have a notion of inclusion, which allows us basically to define a whole structure of increasingly coarser refinements. Things get a little bit tricky when you get into prop, where here you basically need to redevelop a bit of meta theory, but we work essentially up to set we define it, the refinement as set inclusion up to the notion of refinement that is defined on the implementations. All right, I definitely been too slow, so let me speed up a little bit. My apologies for that. To read about instruction, one thing I just want to tell you is that we could unfold everything computes. So we could unfold the representation, get back down to the trees, and reason about the trees. We actually started doing that. It was intractable. So we introduced a whole layer of abstraction where each instruction has some kind of elementary proof rule, which allow us to make the representation function completely opaque and really reasonable at the level of PIR. What I want to convey as top-level message is that it gives us two kind of reasoning principles that we are going to manipulate. First, up to this strong equivalence at the VIR level, we get equations about the syntax structure of the language, over the control flow, and over the instruction, expression, and terminators. And this gives us a symbolic interpreter that we can basically use to step by rewriting in the midst of any refinement proof. And on the other side, we still have this primitive relational logic that supports weakening, that supports all the classical logical combinators over the post condition. And that means this rule for sequential composition, which will be the key ingredients to real positionally refinement proofs during when we consider a compiler. So in a few minutes, let me give you a primer of how we validated this approach. So Spiral is this existing DSL for high-performance numerical computing that Vadim Zaliva doing his PhD has formalized as HELIX in Coq. So it has a whole chain, a whole pipeline compilation where the approach for most of the upper part of the pipeline was to use Spiral as an oracle to perform translation validation. But eventually it goes down to a certain language, FH code, no matter its name, and compiles them to VIR, so to the formal version of LLVM IR. And here we prove a more traditional verified compiler, except that we interface ourselves with FH code by defining an equivalent denotation based on trees, equivalent to the interpreter that they already had, and we will use these techniques to prove this verified compiler. We just look at the structure. We have once again this compilation, phase of representation, interpretation of both sides, so that we get essentially some structure that we can compare. It's both trees, and we will craft this simulation relation that will allow you to prove the refinement. Except that, compared to traditional approaches, we have a few interesting points. First, each subroutine of compilation has its own independent refinement proofs. This stems from the fact that we have no problem denoting sub-open programs on the VIR side in particular. There is no need for a global simulation relation. You can have, you can weaken it locally as need be, or strengthen it locally, I guess, further. The reasoning is performed at the memory level. We saw that we have this hierarchy of refinement relations, so we can actually stop at the memory level and not bother with the non-deterministic part of VIR because the compiler itself doesn't introduce any of these constraints. Crucially, the invariance only has to talk about how the memory relates, so the interesting semantic stuff doesn't have to bother with keeping the prime counter or whatnot. And essentially, the way it works is that on each side, as long as we have concrete instruction, we do symbolic stepping. What we get to parametric statement, well, either it's a recursive subcomponent, in which case we can match things through the sequencing rule by induction, or it's a sub-syntactic component, in which case we can invoke one of the lemmas that we put here. And this is almost done. We basically did every difficult part that we identified, but we still have a little bit of concrete work for a couple of operators. It can be found online at this address. It has been definitely a good use case for us to develop the meta-3 here. I will conclude with this, just with this wrap up. If any of these stories interest you, you can either be interested in interaction trees for your own project or interested in contributing to Velum. Both cases, we'll be very happy to discuss with you. And these are a few next steps that we are thinking about. But in particular, let me emphasize that Lucas Silver will talk about Dijkstra monads forever, which are a way to define the generic framework to define relational logics, program logic, sorry, over ITrees. Thank you very much. I am right on time, so sorry I didn't leave much time for questions, but I will be at the very least available in other rooms as long as need be. Thank you.
Thank you, Yannick. So indeed, it's supposed to be the end of your slot, but we now have break that we can shorten a bit to take a few questions live. Any question?
There is no question. People can enjoy the break, really.
No question in the chat.
I have a short question.
Sure.
I'm very interested. I dropped into the talk halfway, so I missed a bit. What is the closest publication or written thing that I can read if I want to catch up?
Right, that's an excellent question. So if you are interested in I3s themselves, then it's our last year POPL paper. Associated, if you're specifically interested in co-induction, but it's more niche, then there is a CPB paper on Chicago. If you're interested in Velum, so the second paper is called Generalized Parametric Co-induction or something at CPP. So these are about I3s themselves. When it comes to Velum, to VIR, it's not yet published. We have one paper about the design of the language itself that is currently under submission. If you're interested, we'll be happy to send you the draft, of course. And we are about to wrap up a second paper about the proof effort for HELIX, but this hopefully should be fully written in 10 days. We'll be happy to send you the draft in 10 days.
I think I can wait for the official release, but thank you for the offer.
Of course.
So the homepage for Velum is a little bit outdated, is that correct? Because the last publication there is from 2017.
That probably makes sense in the sense that so the main page for Velum would be the GitHub. That's the main one we've been using. But you're right that there hasn't been a written publication. We hope there will be a publication in 3 weeks, but it's still in the pipe. I don't think that Steve has associated the I3 publication to Velum explicitly.
Okay.
Part of a more general project.
Right. Okay. Thank you very much. And thanks for the talk.
Thank you.
Any other question?
Hi, can I ask a question?
Sure.
Yeah.
So let's say I want to reuse the backend from CompCert, for instance, to have a verified comparer from VIR to assembly. What would be the best way? Would be to rewrite CompCert using interaction trees, or can we have something that can go from interaction trees to small step semantics?
Yeah, that's an excellent question. So there's kind of two parts. I would say that if you want to use the backend from CompCert, you definitely do not want to rewrite everything with trees. I don't think that would be wise. We are, I don't know if I will be involved myself, but in particular, Kevin Beck is interested for sure. With Steve on writing a backend for Velum. So this will be using trees. However, what you can do, but it can be hard, arbitrarily hard, I believe, is to write some kind of glue, which is to say that's what we did for HELIX. HELIX already had the semantics, that was operational. We wrote an equivalent semantics with I3s. We just proved here that they were equivalent in a certain sense, so that we could interface ourselves with HELIX without touching anything of the previous passes. However, HELIX is it's complex. It's a quite realistic language. It's complex in size in many ways, but it's fairly simple in the sense that it is strongly normalizing. So that simplifies a lot of things. To write an equivalent I3 semantics for CompCert, I think would be hard, but I would really be interested in looking at what it looks like. I don't see any reason why you can't, but I have no idea what the proof will look like, and I suspect it will be hard. I'm not sure, but I think that Peter from Seoul National University and some of his PhD students have looked into this, but I haven't talked about it with him. So, but they might know more about it. Thanks.
Okay, so I think it's time to end the session. The discussion thread associated with the talk on Clouder will remain active for at least the whole day today, and the discussion will be stored by Clouder. So do not hesitate to ask more questions afterwards or discuss this further on this chat. So we now have a break and we'll resume at 4 on a different Zoom meeting. So click again on the appropriate link you received or on the corresponding button on Clouder. See you.
Thank you.